Hello everyone. Today, I would like to introduce the servo controller from Citron. This is 5-volt serial device that features 8 servo channels, allowing you to control your servo motors serially using USB TTL or COM port. To get started, let's power up the device and connect it properly. To power the servo controller, you will need to connect it from the serial header to your computer. Let's begin with the connections from the serial header. Insert the connector into the serial header on the SC08A board. If you find it difficult to read the labels on the board, don't worry. I've prepared a diagram with the labels to make it easier for you to follow along. Next, we will establish the power connections. Before we proceed, I will show you a clear view of the important board labels by displaying them on the camera output. This is the SC08A servo controller. This is the USB TTL. Connect the red jumper wire from the header, labeled 5V, to the 5V pin on your USB TTL. Now, connect the blue ground wire to the ground pin on the USB TTL. After that, let's set up the data transmission between the SC08A and the USB TTL. Connect the yellow wire, transmit or TX, to the receive data pin RX on the USB TTL. Connect the white wire, receive or RX, to the transmit data pin TX on the USB TTL. This setup ensures that the data sent from one end is received correctly at the other end, establishing a reliable communication link. After that, insert the USB TTL on your computer USB port to power the servo controller. Finally, remember that to power the servo motors, we will need an external power supply. Utilize the power terminal block on the servo controller board to connect your external power source, such as a battery or a power adapter. In my case, I will just use my 5-volt power adapter. I have it wired correctly with the labels on power terminal to the DC power adapter. This will power up servo motors. I have already assembled my pan tilt servos. Now we will insert the servo wires to the servo controller's channel. For our pan or X-axis servo, we will insert it to channel 1. Make sure to connect each 3 pins correctly. Check board labels to prevent any damage. Also, for the tilt or Y-axis servo, we will assign it to channel 2. That concludes our hardware demo on wiring up the servo controller to the computer. We are now ready to do the coding. Let's proceed. Hello and welcome back. In this video, I'm going to show you on how to create a person tracking using Servo with Servo controller from Citron. We will be using OpenVINO environment since it has optimized models for CPU inference. This code will run on OpenVINO 2022.3 API. First go to this GitHub page Glenford49, model_zoo. And download the zip files. Click OpenVINO Detector 2022_3. Then click Download button. Then navigate to Download button and click. I am using Ubuntu Linux. Depending on what operating system you are using, just do the same. Click the folder icon and navigate to Downloads folder. In Windows systems, navigate to Downloads folder. You must have your downloaded zip files. Select the zip files. Then right-click, and click Extract. Open your favorite editor. In my case I will open my VS Code. Then clicking the folder for the extracted files earlier. Dragging OpenVINO Detector 2022_3 folder into my VS Code editor, and it's now my working directory. If you don't have a terminal below, just click the Terminal tab above. And click New Terminal, so that you can't start installing the required packages. First we will install the required packages needed for this program. If some packages or modules are not on your system, just issue the command pip3 install name of package. If you want to use or install the package for system-wide, then the command is sudo pip3 install name of package. Note that using pip3 means that you will be installing the package in Python 3 environment. We need to install OpenCV-contrib Python and hit enter. Then we will install OpenVINO == 2022.3.0 and hit enter. Next we will install PySerial and hit enter. In VS Code New File tab, click the New File icon and write servo pos reporting.py and hit enter. This is the file where we write our servo tracking program. Now let's start coding. First we will import the necessary libraries. Import serial, import logging, and import time. Import numerical Python numpy as np. Then we will declare our servo class. Then we will define the constructor method of class for new instances, which takes an optional parameter uart. Use COM1 or COM3 if you are on Windows system. We will initialize our baud rate to 9600. Then we will initialize our serial device with baud rate 9600. We also initialize our serial 1 with baud rate 9600. Also we will initialize our serial 2 with baud rate 9600. We define our X position equals to 4000. This will be our X position report variable. Also our Y position equals to 2000. This will be our Y position report variable. We will initialize our max distance equals 640. Then we will discard all input buffer in our serial device. We also have to discard all output buffer in our serial device. Printing debug message indicating that the servo motor controller is initialized. Calling the method to activate all servo channels, using parameter all, and a value equals 1. Positioning the X servo to a defined X position value, with a lower speed. Also positioning the Y servo to a defined Y position value, with a lower speed. Adding a time delay execution for 2 seconds. Allowing time for the servo motors to reach the initial positions. Let's create a function to control a servo channel, desired position, velocity, and distance. We define speed which map distance to a new range which is 5 to 250. We will limit the speed up to maximum of 250. This line constructs the first byte of the command packet, with the hex value and channel value. This line extracts the high byte of the 13-bit position value. Also this line extracts the low byte of the 13-bit position value. Bytes function is used to convert a list of integers into a byte sequence containing the first byte, high byte, low byte and velocity. Then we will call the function to read the current position of a specific servo. This function will be responsible to update our servo reporting variables. We will create that afterwards. Then we will send the command to servo controller to move a specific servo to a specified distance. We will discard all input buffer in our serial device. We also have to discard all output buffer in our serial device. Next, we will create a scaling function for servo steps. We will define max steps equal to 0.07. If distance diff is greater than 44, we will calculate for additional steps. Then we will update the max steps plus the calculated additional steps. We will limit the max steps by taking the minimum of max steps with the cap variable. We will define scaling factor to interpolate the diff value between the range 0 and 640. And maps it to the new range 0 and max underscore step. Finally, we will return the scaling factor. Next, we will create a method to parse data, extracting the X and Y values only. This line will find the index of X characters. This line will find the index of y characters. These line extract the numbers following x in the data string, and convert it to integer. Also these line extract the numbers following y in the data string, and convert it to integer. These line call the pan_servo method, with the extracted x value as arguments to control the x servo motor. These line call the ~servo method, with the extracted y value as arguments to control the y servo motor. Let's now create a function responsible for servo position reporting. First we will define uart. If channel is equals to 1, we will set our uart is equals to uart1. If channel is equals to 2, we will set our uart is equals to uart2. We will assign the first byte to hold the control command and channel number. Then first underscore byte is sent over the uart channel using the uart_write method. Then we will read the high byte first. Also we will read the low byte, which both contain position information. Then we will combine the 2 bytes into a single integer value for position information, and assigning it to reading position variable. If channel is equals to 1, we will update our servo x position to the reading position. If channel is equals to 2, we will update our servo y position to the reading position. Now let's create a function for the movement of our x-axis servo, which take a single parameter from the result of data parsing function we have created earlier. If data less than 4000, we will define diff is equals to 4000 subtracted by data. Then we will define our data x equals to diff multiplied by the result of calling the function calculate scaling factor with arguments diff. Finally we will call the function to move our x servo to a desired position by adding the previous x position plus the data x and the distance difference. Else we define diff equals to data subtracted by 4000. Then we will define our data x equal to diff multiplied by the result of calling the function calculate scaling factor with arguments diff. We will move the x servo to a desired position, this time by subtracting the previous x position with data x and with arguments distance difference. Let's now create a function to move our y-axis servo, which takes self-parameter and data from the result of data parsing function we have created earlier. We will define cap as our limits up to 0.07. If data less than 4000, we will define diff is equals to 4000 subtracted by data. Then we will define our data y equal to diff multiplied by the result of calling the function calculate scaling factor with arguments diff and cap variable. Finally, we will call the function to move our y servo to a desired position by adding the previous y position and data y with a diff variable for speed. Else, we define diff equals to data subtracted by 4000. Then we will define our data y equals to diff multiplied by the result of calling the function calculate scaling factor with arguments diff and cap. We will move the y servo to a desired position, this time by subtracting the previous y position with data y with a diff variable for speed. Now let's create function that is responsible for turning on or off servo motors. If channel is equals to all, we will write the control byte to activate all channels. If using specific channel, we will assign first byte equals to control byte with channel number. Then we will write the control byte together with specific channel and activate it. I have this commented line to initialize the servo class with the USBTTL. This line moves the servo X to a desired position. This line moves the servo Y to a desired position. Uncomment it if you want to use it. Finally, let's run this code to see if there's an error. There's no error on our code. Let's proceed to person detection coding. Now we will develop our person detector and integrate the servo class we created earlier. Let's click the extracted detector py. First, we need to import the necessary libraries. Import Computer Vision Library, CV2. Import Numerical Python, NumPy as NP. From OpenVINO runtime, import core, and also import partial shape. From Model API, Performance Metrics. Import Performance Metrics. You should have this folder in your working directory. From time, import perf counter. Then we will import servo class from servo pos reporting we created earlier. Then we will initialize OpenVINO API, core equals core. Next, we will load the person, vehicle, bike detection model into memory. Then, we will read our detection loaded model. Getting the input layers of the loaded model. Also, getting the output layers of the loaded model. We will create a model size variable for model reshaping. If model size is greater than 0, then we will reshape or resize our model based on the variable model size. Note that resizing the model into smaller value will increase the processing speed, but the trade-off is accuracy. We will select CPU as our device. If you have NCS2, you can change it to Myriad. Note that here you need Intel CPU or NCS2. Then compile the model for a specific device. Here, we can use NCS2, GPU, or CPU. Next is creating a variable cap for video capture object. In this case we will be using our webcam. Then we will be defining the input layer shape as N, C, H, W. Defining metrics from performance metrics class. Then we will initialize our servo variable from servo class. Also we will initialize our x and y equals to none. And our color equals to neon green. We also initialize the center, frame height, and the frame width equals to none. Next, we will create a function named Crosshair, which takes parameters frame, center points and width. We will set global x and y variables. Then we define our center x and center y equals to center points. Also we define our radius equals to width divided by 2. If x is equals to none, means this is the first iteration. We will modify the value of y equals to y-axis of frame divided by 2. Also we will modify the value of x equals to x-axis of frame divided by 2. If the absolute value of y minus cy is less than 25 and the absolute value of x minus cx is less than 25, we will create circle of our crosshair, which vary depending on the width of the object. Then we will create horizontal left line inside the circle. Next we will create horizontal right line inside the circle. Also we will create vertical upper line inside the circle. Finally we will create vertical lower line inside the circle, thus creating our crosshair that vary its size depending on the objects detected. Next we will create a rectangle filled with red color in upper position of our crosshair, and a text labeled as target locked, with black color. Our crosshair function is already done. Let's now create a function named feedServo which return a center point to be feed on servos, which take three parameters: center X, center Y and frame. Using the NumPy linear interpolation, we will define servo X to map the center X value from frame shape value to its equivalent value on new range 0 to 8000. Also, we will define servo Y to map the center Y value. Then we will define data to hold the formatted string of servo X and servo Y placeholders into integers respectively. Lastly, we will return the data. Let's create a function to measure the Euclidean distance of an object from the center, which takes the parameters of object list and a center point. If box list is empty, we just return none. Then we will define our object list as the converted box list to a NumPy array. We also convert our center to NumPy array and assign to a variable center. We calculate all centroid X from the object points. We also calculate all centroid Y from the object points. Using the NumPy column stack, we will form the centroids from centroid X and centroid Y. Then we will calculate the difference between centroids from the given center. We now calculate the Euclidean distance for each object from the given center. Using the NumPy argmin, we will find the index of minimum nearest distance. Finally, we will return the index number. Starting the main loop of the program. Defining start time needed for FPS calculation. Next is reading the video, frame by frame. If center is equals to none, then we will modify the value of center to half the size of frame X and also half the size of frame Y. We also modify the frame height, frame width from frame shape. We should resize the frame before feeding it to our model. Pre-processing the data before feeding it into a neural network, changing the layout of the dimensions, and adding an extra dimension. Then, we will create request with compiled model, prior to inference. Invoking the inference request with the provided input data, where the input data is associated with a specific input layer of the model. Retrieves the output tensor data from the specified output layer of the model within an inference request. Then we will define boxes for object bounding box list as an empty list. defining servo data equals to none. Then we will iterate over the detections in result index 0 subindex 0 and performs the following operations. Next, we will extract the label from each detection. Also, we will extract the confidence score from each detection. If the confidence score is greater than 0.69, and label is equals 2, which is equivalent to a person, we will convert the normalized x-minimum coordinates of the bounding box to pixel coordinates from frame dimensions. Getting the normalized y-minimum from frame dimensions. Getting the normalized x-maximum from frame dimensions. Getting the normalized y-maximum from frame dimensions. Next, we will append the detection box of an object to boxes list. Using the CV2 rectangle to draw the rectangle of every detected person. Using CV2 put text to show the label of every detected person. We will define variable nearest to hold the index number by calling the Euclidean distance function we created earlier. If nearest is not equals to none, means there is a detected object. We will draw a red rectangle of the nearest detected person from the boxes list. Then we will now define the center x-axis of the nearest object, and assign it to center x. We will also define the center y-axis of the nearest detected object, and assign it to center y. Next we will define the width of an object detected. Then we will call the feed servo function with the arguments of the nearest of person center x and center y, and assign to a variable servo data. Then we will now call the servo data parsing, which is responsible for moving the servos to track the detected person. Then we will call the function to draw crosshair on the object. Using the NumPy linear interpolation, we will define xCore to map the pos x value from servo class, which has range value from 0 to 8000 to its equivalent value on new range 0 to 180. Also, we will define yCore to map the pos y value from servo class, which has range value from 0 to 8000 to its equivalent value on new range 0 to 180. Assigning a pos variable to hold the formatted string of xCore and yCore. Using CV2 put text to draw servo position in an image, with black color and a thickness equals to 5. Drawing another servo position, this time with a yellowish color and a thickness of 1 to highlight the text. Updating the FPS with metrics update. showing the output window of every frame. Creating a variable for wait key. Breaking the loop if Q or escape key is pressed. Releases the video capture object. Closes all the windows created by CV2mshow. Code execution ends. That concludes our person detection and servo tracking coding. Without any delay, let's fire it up. As you can see, it draws the detected person's bounding box, and the servo tracks the person wherever it goes. And FPS